Sebuah kilang kawasan perindustrian di Jeneram Hilir, Sepang disyaki milik punca pencemaran di sungai.
The culprit behind the pollution that caused unscheduled water cuts in parts of Selangor and Kuala Lumpur is a repeat.
All states in Peninsular Malaysia have been categorised as highly polluted.
Dalam itu, Malaysia menegaskan ia bukan kali pertama pencemaran sungai berlaku disebabkan kilang berkenaan.
So today, our team visited the Department of Environment DOE Shah Alam. We meet a DOE officer to seek his professional opinion regarding to water sample that has been taken to relate with the water quality index WQI. So since the recording not allowed, so I will pass to my partner Adam to discuss in detail about the output or outcome about the discussion. So Adam.
Okay, thank you, Kawi. Based on our discussion with an officer from the Department of Environment, we were informed about several important aspects of water quality assessment and turbidity reduction. The officer explained that the water quality index, or WQI, which is the most important way to solve turbidity problems, is through the jar test, which helps determine the best coagulant type and dosage. This test also helps identify the amount of sediment, turbidity, and color in the water, ensuring the treatment process is effective. In addition, the officer highlighted that pH monitoring is important because it affects coagulation performance. Maintaining an optimum pH range improve floc formation and settling. The turbidity meter is then used to check water clarity and evaluate how well the treatment works. Overall, turbidity reduction mainly depends on proper treatment, and the critical parameter to achieve effective water treatment are turbidity, pH, and coagulant dosage. So that's all from our discussion with an officer Department of Environment.
Assalamualaikum and salam sejahtera. We are currently at one of the potential location which is near to the printing factory. Today we are taking the water sample to conduct the water quality index experiment, WQI. There are 6 WQI. The first one is biochemical oxygen demand, BOD. The second one is chemical oxygen demand, COD. The third one is pH, dissolved solid, dissolved oxygen, total suspended solid, and the turbidity test. Okay, right now we are taking the water sample. As you can see, this is how we take the water sample. First step of procedure jar test. 6 beakers were each filled with 100 ml of water sample and labelled accordingly. Six coagulant solutions were prepared with increasing alum dosage. 1 beaker was used as a control sample, while the others received alum dosage ranging from 2 ml to 10 ml. The beaker were placed on the jar test apparatus and the pedals were positioned properly. The measured alum dosage were added to the respective beakers. The stirring machine was switched on. Okay, the first step is repeat mixing was carried out at 140 RPM for 3 minutes and followed by slow mixing at 40 RPM for 3 minutes. After mixing, the sample were allowed to settle for 20 minutes. The stirring machine was switched off and a small amount of water was carefully taken from each beaker. The turbidity and pH of each sample were measured using a turbidity meter and pH meter, and the results were recorded.
For the procedure, first, we switch on the turbidity meter and let it get ready. Then the sample cell is rinsed with distilled water to make sure it's clean and no contamination. After that, we measure 10 ml of the water sample using the measuring cylinder. The water sample is poured 45 degrees into the sample cell carefully, making sure there are no air bubbles inside. Next, the outside of the sample cell is wiped using a clean cloth to remove any fingerprints or water drops. Once it's clean, the sample cell is placed into the turbidity meter properly. The turbidity meter reading is then taken and recorded. Finally, the same steps are repeated for the rest of the water sample. This graph shows the variation of turbidity before and after the jar test with different alum dosage. The initial turbidity remains constant at 16.5 NTU for all beakers, indicating that the raw water quality is uniform before treatment. At a low alum dosage of 2 ml, the final turbidity increases to 23 NTU, resulting in negative turbidity removal. This occurs due to insufficient coagulant addition, where the suspended and colloidal particles are not effectively destabilized. As a result, incomplete floc formation occurs and fine particles remain suspended in the water during the mixing process. This behavior is commonly associated with underdosing of coagulant in coagulation theory. As the alum dosage increases from 4 to 6 ml, the turbidity begins to decrease. The final turbidity reduced to 17.7 NTU at 4 ml and further decreased to 14 NTU at 6 ml. This indicates that sufficient alum is available to neutralize particle charge, allowing particles to aggregate into larger flocks that can settle more effectively. At higher alum dosage and 4 and 10 ml, the turbidity removal improves significantly. The lowest turbidity value of 7.76 NTU is achieved at 10 ml, corresponding the highest turbidity removal of 52.97%. This indicates that 10 ml is the optimum alum dosage for turbidity removal in this experiment. Overall, the result demonstrates that increasing alum dosage enhances coagulation efficiency up to an optimum point. This trend is consistent with the standard water treatment principle discussed in environmental engineering reference and guidelines. Therefore, optimizing of alum dosage through jar testing is essential to achieve effective turbidity reduction in water treatment process.
Step 1. 10 ml cylinder sample cell was rinsed thoroughly with distilled water to avoid any contamination from previous sample. Step 2. The same sample was filled with distilled water about 10 ml. Step 3. The 10 ml cylinder sample cell was filled with the treated water sample, ensuring that no air bubbles were trapped inside, as bubble could affect light transmission. Step 4. The outside surface of the sample cell was wiped with a clean, stain-free cloth to remove fingerprints, dust or water droplets that could interfere with the reading. Step 5. The spectrophotometer was switched on and allowed to warm up to ensure stable and accurate readings. Step 6. The instrument was calibrated using distilled water as a blank reference to eliminate background interference and to set a zero baseline. Step 7. The sample cell was carefully placed into spectrophotometer, aligned properly, and the color reading was recorded in standard color units TCU. Step 8. Repeat step 6 to 7 for the remaining 5 treated water samples obtained from the jar test. The jar test results show that alum dosage has a strong effect on color reduction. The initial color of the raw water was 161 TCU for all samples. At a low dosage of 2 ml, the color increased to 257 TCU, indicating underdosing and ineffective coagulation. When the dosage was increased to 4 and 6 ml, the color decreased to 146 TCU and 109 TCU, showing improved floc formation and removal of colors causing substances. Further, increase to 8 and 10 ml reduced the color to 96 TCU and 77 TCU, with the best result at 10 ml. This showed that increasing alum dosage improved color removal up to an optimum level. Overall, 10 ml was identified as the optimum dosage for maximum color reduction.
The pH probe is rinsed with distilled water to remove any contaminants before measurement. Make sure that the pH meter is switched on, then the probe is carefully immersed into the first beaker containing the water sample, ensuring that the sensing tape is fully submerged. Next, the pH reading is allowed to stabilize until a steady value is displayed or an indicator sound is heard. So from that, the pH value is recorded and these steps are repeated for the remaining beakers. After completing all measurement, the probe is rinsed again and the pH meter is switched off. This graph shows the variation of pH before and after the jar test with different aluminium sulfate as alum dosages. The initial pH remains constant at 7.22 for all beakers, which indicates that the raw water conditions are uniform before treatment. After the jar test process, the final pH shows a decreasing trend as the alum dosage increases. The pH value decreases from 7.22 at 0 alum dosage to 6.34 at 10 ml alum dosage, with the highest percentage reduction of 12.19%. This shows that the alum dosage has a clear effect on the pH of the treated water. This reduction in pH occurs due to the hydrolysis of alum during the coagulation process. When alum is added to the water, it reacts and releases hydrogen ions, which increase the acidity of the solution and cause the pH to decrease. This behavior is consistent with standard water treatment theory discussed in environmental engineering reference. Despite the decrease in pH, all final pH values remain within the effective range for alum coagulation. This indicates that the treatment conditions are still suitable and do not result in excessive acidity. Similar behavior has been reported in standard water treatment guideline and textbooks. In conclusion, the results show that the increasing alum dosage improves the coagulation process but also lowers the pH due to the chemical reactions in the water. Therefore, pH monitoring during jar test is important to ensure effective treatment performance while maintaining acceptable water quality.
In this study, the optimum coagulant dosage was determined by analyzing the performance of aluminium sulfate at different dosage during the jar test experiment. 1 control sample and 5 treated samples with alum dosage ranging from 2 to 10 ml were evaluated. The results show that the low alum dosage, particularly at 2 and 4 ml, were ineffective and resulted in poor turbidity and color removal due to underdosing and incomplete flow formation. Significant improvement was observed when the dosage increased to 6 ml and above. The highest removal efficiencies for turbidity and color were achieved at 10 ml, while the pH remained within an acceptable range. Therefore, 10 ml of alum was identified as the optimum coagulant dosage for this study.
This section compared the treated water quality with Malaysian National Water Quality Standard and WHO guideline. At the optimum alum dosage of 10 ml, turbidity reduced from 60.5 NTU to 7.76 NTU. This shows clear improvement even though it does not fully meet the WHO limit for drinking water. However, it is acceptable for early stage treatment and surface water improvement. Color was reduced from 161 TCU to 77 TCU, showing that alum was effective in removing color. Although further treatment is needed for drinking use, the pH value slightly reduced from 7.22 to 6.34 due to alum reaction, but it stayed within the acceptable range set by both standards. Overall, the results show that alum treatment is effective in improving water quality before discharge or further treatment.
Despite the positive result obtained, several limitations and experimental uncertainties should be considered. Firstly, the jar test was conducted under laboratory conditions, which may not fully represent real wastewater treatment plant operations. In addition, the study was based on a single water sample collected at one location and time, while industrial wastewater quality can vary significantly. Measurement uncertainties may also arise from instrument calibration, sample handling, and human factors during the experiment. Furthermore, only turbidity, color, and pH were analysed, while other important parameters were not included. Therefore, these limitations should be considered when interpreting the results, and further studies are recommended.
In conclusion, the study showed that the coagulation and flocculation process using alum is effective for treating polluted water. The untreated water had high color and moderate turbidity due to nearby human activities. Jar test results showed that alum dosage strongly affect treatment performance. The best dosage was 10 ml, where both turbidity and color were reduced by more than 50%, while pH stayed within a safe range. Overall, alum treatment is suitable and practical method for improving water quality, and jar testing is important for finding the best chemical dosage to support safe water management.
Bikin pusing, pusing karena umur sudah aman saja mau ngapain mau repot, jangan sampai